mining that I hadn't seen before. I was working around places where we're talking about um, failure and fairly high stresses is core disking. So core disking is definitely a manifestation of fairly high strains, and what it happens is that tensile stresses uh, are present then in the rock as it's cored, and that leads to the core breaking up into little coin-shaped disks. Here's some more terms that are interesting. Strain bursts, or sometimes that term is used by mining and technical people, and in other places it'll be known as rock bursts. And basically, this is a catastrophic or explosive failure of the wall of an underground excavation. In contrast, convergence is a non-catastrophic failure where the walls of the walls of the drive or the underground excavation just slowly move in relative to one another, and that's from pressure in fairly soft rock, or some cases from yield and slow movement along fractures or faults. Maybe the most difficult one to understand, though, is what's known as high stress. So in geotechnical, high stress is typically taken to mean that the stresses are relatively large in comparison to failure. So a ratio, something like the mean stress or the confining stress, divided by the unconfined compressive strength, will be used to discern whether you're at high stress or low stress conditions. And obviously, if the stresses are relatively higher in comparison to the rock strength, you're going to be somewhat closer to failure. So if a geotechnical person says to you, "Well, we've got high stress conditions," remember probably what they mean is that you're talking about a high ratio of stress to strength, and that means that you're more likely to experience, say, catastrophic failure such as rock bursting. In contrast, in rock mechanics, classical rock mechanics, or structural geology, it's often common to define high stress as either high differential stress, which is the difference between the most compressive and the least compressive principal stress, or high mean stress, which is the average of the three principal stresses. So I've just popped a Moore diagram down there at the bottom of the slide to remind you about the difference or what a Moore diagram is. So the two little cubes on the right, the first one shows a little cube somewhere in the rock mass with both shear stresses and normal stresses. And the bottom of the two cubes shows a situation where if you rotate that cube around and try different orientations, eventually you'll find a spot where there's no shear stress on the faces of the cube. And then the normal stresses across the three faces of the cube then are the principal stresses, S1, S2, S3. So the problem of finding the principal stresses in a general case involves essentially finding the orientation of that cube. And then those three faces are known as the principal planes, and the normal stresses across those are the principal stresses. The Moore diagram shown on the right then shows two states of stress, the purple one and the light blue one. And the principal stresses are where those circles intersect the horizontal axis. So S1, S2, S3, higher, more compressive stresses are off to the right. Lower stresses closer to tensile are over to the left. And tensile stresses would actually be negative in the common rock mechanics, mining, structural geology kind of convention. The blue state of stress is going to be a smaller mean stress and a smaller differential stress than that purple one. So just remembering there is a big difference between the way geotechnical people talk about high stress. They use a ratio of mean stress or confining stress or something like that to the unconfined compressive strength. And structural geologists, people doing classic rock mechanics, are going to probably want to know more about, well, where's the intermediate stress, and also are you talking about high differential stress or high mean stress? So another important thing to understand when we're talking about stresses, and it's useful for structural geologists, particularly to understand and think about it. It's quite common in structural geology, but not so widely used in rock mechanics and geotechnical, is what we refer to as the Andersonian constraint. So Ernest Anderson was a geologist with a strong interest in solid mechanics and so on. Lived from Scotland. Um, and his reasoning went something like this: the Earth's surface is a free surface, so it's a boundary between, say, air and rock. And because we don't have any shear stresses in the air, that means the Earth's surface is shear stress free, and therefore it must be a principal plane. And then that means that one of the principal stresses must be perpendicular to that. So if we're talking about atmospheric pressure at the Earth's surface, that means the vertical principal stress at the Earth's surface must be 1 atmosphere, which is essentially 0 in terms of geological stresses. So if the Earth's surface is relatively flat, one of the principal stresses must be vertical, and the other two principal stresses have to be horizontal. So that's Anderson's assumption number 1. The Earth's surface is a principal plane, and one of the principal stresses must be vertical. So I've just put in 2 pictures there to help the discussion along. So in much of West Australia in the Yilgarn Craton, the surface looks something like the diagram, the picture on the left. So it's flat, and the atmospheric pressure is probably very close to 1 atmosphere, and there's no shear stresses. So in West Australia, Anderson's assumption number 1, that the Earth's surface is a principal plane, is probably pretty close to accurate. It's a good solid initial assumption about what the orientations of the stresses are, certainly near the surface. In contrast, if you go to a place where there's a lot of relief, such as Papua New Guinea or New Zealand or the Alps or the Andes or somewhere like that, or places in, say, where you're doing a lot of mining, like, say, big open pits, then the assumption probably doesn't hold true anymore. And then you've got to think, okay, well, this doesn't work. So then the second part of the Anderson assumption is that we're going to assume that there's sort of a standard failure criterion. So we have a little cylinder of rock there undergoing a test where we got sigma 1 and sigma 3, or principal stress is sigma 1, sigma 3, and then we're going to induce a shear failure or a fault in the little cylinder of rock as we compress it. So we know that we're going to expect sort of conjugate orientations, or orientations where the faults that form are at a smaller angle than, say, 45 degrees to sigma 1. So that tends to then be used to infer the orientations of stresses. And this is a common assumption throughout geology, partly due to Anderson, but partly due to just the choice of the failure criterion. So then Anderson's assumption then results in three main principal stress states. And I'll show it in the next slide probably more clearly. So you can ask yourself then, well, which of the 3 principal stresses is the biggest? And we tend to talk about then the vertical stress we refer to as SV, or it's the vertical principal stress, and then we have SH min and SH max, which are the smaller and the larger of the horizontal principal stresses. So then if the Earth's surface is flat and one of the principal stresses is vertical, then we can ask, well, which one of the 3 principal stresses? So if SV, or the vertical principal stress, is the biggest one, we refer to that as a normal faulting state of stress, and we get faults like the top block diagram, fairly steep normal faults. And that's because the kind of faults that should form should be at a relatively small angle, say 30 degrees to the vertical principal stress. If, in contrast, the intermediate principal stress is vertical, as shown in the middle diagram, then we expect strike-slip faulting. The faults will be inclined at about, say, 30 degrees to SH max, which is a horizontal principal stress. Then the third case is if we have the vertical stress is the smallest of the principal stresses, then what we would expect is relatively shallow dipping reverse faults, and that's the bottom diagram, known as the reverse faulting state of stress. Now, when talking about magnitudes of principal stresses in geotechnical engineering, and to some degree in oil and gas, many other places, people will talk about a stress ratio, that is the ratio of the vertical principal stress to the horizontal stress. And it's quite common to use this kind of thing. What it doesn't do, however, is it doesn't necessarily give you an idea what the intermediate principal stress is. And as we've seen in the 3 diagrams, it does matter what's happening with the intermediate principal stress, and you do need to know uh, what the three principal stresses are if you want to fully describe the state of stress. Okay, so let's talk about faults very briefly. Because we often observe increased complexity and deformation or strain near faults, of course we know that stresses are higher near faults, leading to more failure and deformation. Everyone knows that. So here we go. Here's a fault, very famous exposure in the Basin Range of the U.S. We can see rotation of bedding, local folding, multiple fault surfaces, all kinds of complexity along here. So um, we know that the stresses must be higher. Of course. Does anybody have any problem with that? Well, it turns out I'm going to argue that, well, this is probably not the case. This is potentially, you're telling part of the story if this is the way you think of faults. And the reason is that, well, uh, faults really are flaws or weak features in the Earth crust. So faults really come into being to reduce the strain energy. So if a fault could talk and you asked it what it was doing, it would say, well, I'm going to fail and I'm going to reduce the strain energy. I'm going to slide this way, and then some energy will be released, and the rock will all be happier. So although we see these complexities near faults, the important thing to remember is that the deformation and the extra deformation and so on is episodic in time, as in it doesn't happen all the time. And it's also not constant across the area of the fault. So uh, little crunchy parts happen along faults, but they're just a small proportion of the entire fault surface at any one time. And that's what leads to the complex, highly deformed material right around a fault. But it's probably wrong to think that faults just magically cause extra stress near them. Probably what's happening is the faults are actually relaxing the stress and letting things smooth out or get happier in a sense because the difference between the principal stresses is getting smaller. So that's the end of the introduction and part one. I'll continue on in part two, so just find the second video and get started in there. Okay, thanks.